Hello. This is video 42, I believe. Yes. And we need to look at Roman numeral 2, continuation of the last video. This is the other major, the competitor way to represent a graph. Adjacency lists. A-D-J-A-C-E-N-C-Y lists. And I'll do this by example. For example, for graph G1, the ungraph, undirected, unweighted, we do need to represent all the nodes. And one way to do that is to put all the nodes in an array of nodes. We've got Amazon, eBay, Facebook, all heavily abbreviated, except eBay. I can write all that. Facebook. Who's next? Google, Transylvania, Twitter. Now, I've got these in alphabetical order, and I kind of regret that almost now, because this is a set of nodes. There's not really any significance to them being in alphabetical order necessarily. That kind of depends on the application where we're using this graph. So if you want to scramble these up and put them in a different order, that's fine. But since this is an array, I'm going to make use of the index numbers. This is 0, 1, 2, 3, 4, 5, 6, and we'll say that that's all. We're not going to have, even though I got dots, that means I've got space for other nodes, but this is all that was in this particular data set. Lists. That sounds like a singly linked list. I know how to do a singly linked list. Well, Amazon, I've got this list written down as 3, 4, 2. And if that violates your sense of equilibrium or whatever, because those are not in any particular order, don't let that bother you. Adjacency, this list, this doesn't say I can go from node 0 to node 3 to node 4 to node 2. It says that actually these three are a set of nodes. That's why I, on purpose, put them out of order. They're not necessarily a sequence. Again, depending on the application, maybe I do want to keep them in increasing order. But all this says, if from Amazon I can go directly to Google following one arc, it's adjacent. From Amazon I can go to Transylvania, one arc. From Amazon I can go to Facebook, one arc. It says that these three index numbers are the index numbers of the places that I can go following one arc. And aside from not using up all my purple ink, if you're wondering, well, why do we use these index numbers rather than the whole thing? These labels here in their nodes, everything depends on the application. We could have a value type that is really big. Maybe this Facebook node, for example, has the names and the mini biographies of the founders, and it has how much money they've made each of the year, the last 10 years and stuff. This could be a very large piece of data here. And we don't want to replicate that through all the different places where it might show up in the adjacency list. So the simplest way to do it, the most direct way to do it, is whenever we need to represent Facebook over here in the adjacency list, just use its index number. That's always going to be a small finite size. It's the same general principle. It's why we pass constant references as parameters to functions, so that we don't take up a huge amount of space in the stack. Here we don't take up a huge amount of space in our data structure, the representation. I hope I made a clear enough case for that. eBay goes to 3, meaning 3 is the only thing in its adjacency list. Facebook, 3, what else we got? 3, 0, 6. Again, that's a set of 3 nodes. From Facebook, I can go directly to whom? Google. I can go to Amazon. I can go to Wikipedia. Okay, moving right along. Google can go 0, 1, 2. Transylvania goes 0, 5, 6. Double check these against the picture of graph G1. This is an alternative way to represent it. Twitter, 4 and 6, I believe. Wikipedia, 2, 5, 4. Now, this at least one more time, undirected, unweighted. What are the philosophical implications of this being undirected? Well, Every arc in the graph shows up in this representation twice. It better, or I did it wrong. Google, from 3 I can go to node 1. So node 1 better have 3 in its adjacency list. Node 1 does have 3 and nothing else. That was fun. Let me do that again. Twitter has 6 in its adjacency list, and Twitter is 5. So 6 better have node 5 in its adjacency list, and in fact it does. So here's the weird deal. A realization all of a sudden. An undirected graph is actually a special case of a directed graph, where we have an arc going each direction. That's why every arc here is represented twice. We can think of it as an arc that goes from A to B. We could alternatively think of it as an arc that goes from B to A. So that is a weird thought, isn't it? If we've got a good, solid way to represent a directed graph, we don't have to do anything special to represent an undirected graph. We just put every arc in there forward and backward. And voila, we don't have to change any of our code. We just have to know in advance that it's going to be undirected, so that we've got to store A in B's list and B in A's list. What's the implication of it being unweighted? Well, unweighted actually makes the adjacency lists over here easy, because all we got to know is the destination node. We don't have to know anything else like the weight or the airline or the number or anything. So these can be simple linked lists of integers. And you've probably, I keep saying, you've probably already figured this out, but I'm sorry, I won't say it this time. I'll figure it out for you. Why are there only 2? Roman numeral 1, Roman numeral 2. The age-old battle, the battle of the ages. This is our, what? Unbounded case, like a linked list. The other is the bounded case, like an array. It's just a 2-dimensional array rather than a regular array. The other one has a preset max, entries for all possible arcs, whether they're filled in or not. This one, we dynamically allocate information for an arc on the fly. It's unbounded, an arbitrarily linked list. They're all different. And I said it, but it's such an important concept that I'm going to say it in blue on the board. This is a set of nodes. And I say that because the picture, until you get used to it, the picture can be misleading. This really does look like it's describing a path from node 0 to node 3 to node 4 to node 2. It is not. It's actually 3 separate paths of one arc, from 0 to 3, from 0 to 4, from 0 to 2. So 3, 4, and 2 is the set of nodes that are adjacent to Amazon. Okay. I do not know what else to say about that, except now all of a sudden you are in the way, and I should get rid of you. Still talking about adjacency lists. And here is trusty purple, G2. We're still going to take all the information we need to know about a node and put that in some possibly small, possibly huge data item array here, and label them 0, 1, 2, 3, 4, 5, 6. For quick access, I don't think there are 6, are there? There are only 5. That's okay, I won't use all of them. A, B, C, D, E, F. That's the first letter of each one of those trancy buildings. Yeah, that wasn't an accident. I did that on purpose. Okay. From A, I can go to, in my graph, I can go to node B, which is node 1. I can also go to node 3. Now then, those arcs, I should keep those pictures handy. Those arcs in graph G2, G2, there. From A, I can go to node B, which is VSC. And from A, I could go to 3, which is Dalton Voigt. There's something missing, though. First of all, well, for reference, while you're thinking about what's missing that needs to be represented in this graph, this is directed, but it's also weighted. Directed means, okay, from A I can go to 1. That does not imply that B is going to have an arrow here going back to node 0. Remember, directed graphs are not symmetric as a rule. So that does not imply that. Here's the kicker, weighted. Somewhere I've got to represent that it takes me 20 minutes to go from A to B, and I got to represent that it takes 10 minutes to go from A to D. Now then, 20 minutes. Should that go with this? Is that an attribute of the node, the 20 minutes? Well, no, I can't do that because this one is not 20 minutes. From A to D is 10 minutes. And I can't put, unless I start an array of weights, but then I won't know which nodes they go. Oh, it's going to be confusing. What am I leading you toward, or I hope I am, perhaps feebly? The weight is an attribute of the arc, not an attribute of the node. Where in this data structure is something that represents an arc? Well, these are not simple integers anymore. This is going to be an adjacency list of a different data type. We will have a node structure that represents the actual nodes in the graph. We need a separate structure now. In the general case, we need a separate structure to represent the arc, because there's more than one thing that we need to know about the arcs. In this case, we need to know that the destination of this arc is node B, but we also need to know that it goes with a weight 20. I'm going to do that in a box. You can put it in a circle, you can put it in a box, you can put it in a triangle, whatever. But I'm just distinguishing this. This is two different pieces of data that I'm going to have to know about this one specific arc. And the stuff that needs to be known about an arc is going to have to be what our list, linked list or ordered list or whatever it may be, what our list consists of. Okay, that was a lengthy description. From A to 3, I can get there in 10, so I'm going to put 10 in a box. And all of a sudden I realized I didn't make this tall enough for me to do this very well. But here we go anyway. B can go to, I can't even read my own writing, I think that's 2 with a weight of 15. Double check that against graph G2. It could also go to 3 with a weight of 15. From C, I can go to 1 with a weight of 7. Actually, you know, it would have been wiser, now that I think of it, to make it a box with 2 different fields in it, because really you're just going to have one structure there that represents an arc, just like we've always had one structure that represents a node in a list or in a tree or whatever. But this is just a diagram. This is not really that close to implementation yet. D goes all over the place. D can go to 2 with a weight of 2. Also, remember, these arrows represent alternatives, not a pathway. D can go to 5 with a weight of 10. And D can go to 4 with a weight of 5. Where the number above that seems to be disembodied floating in space out there, that's the destination node. We're still representing those by index numbers for the same reason. We don't want to have to replicate all the data about D every time 3 showed up over here in an adjacency list. We don't really have any way to sort of get clever about the node data. I mean, the arc data, because the arc data is going to be different for every single arc in the graph in the general case. We can't reuse that the way we reuse the index numbers over here. A couple more. E can go to node 2 with a weight of 8. And F can go to node 2 with a weight of 1. I wish I had double checked this one more time. I actually did double check it. I just don't trust myself. I don't always catch the errors. So please compare this to your diagram of graph G2 and see if you can make intuitive sense of all the information that's written over here. Let me browbeat you with it a little bit. This list right here doesn't mean I can go from node 3 to node 2 to node 5 to node 4 in one direct path. Maybe I can, maybe I can't. But that's not what this list tells me. This list tells me I can go from D to 2 with a weight of 2. I can go from D, also known as node 3, to 5 with a weight of 10. I can go from 3 to 4 with a weight of 5. That's the information that's in the graph. And if it's still bothering you, you've got to sort by something. That should either be 2, 4, 5, or it should be 2, 5, 10. Either sort by the weights or sort by the index number of the node, sort by something. Well, not necessarily. In the general case, this is a set of 3 arcs. You might very well want to go back and use that ordered list that you used at the very beginning of this class and order it either by the weight or by the node number, but that depends. How many times have I said this in the last few videos? That depends on the application. This is still supposed to be just a general representation of all the information that's in the graph. And now that we have all the information that's in the graph in different ways, bounded and unbounded, weighted and unweighted, directed and undirected, now we need to focus and see if we can get busy on what we actually need for what we are actually going to be doing. I'll see you online.